So welcome everyone to this week's One Word Mathematical Physics seminar. And this is a regular seminar series of IAMP, the International Association of Mathematical Physics. We have a seminar every Tuesday at exactly the same time, UTC 14. And you can find more about the seminar series in our webpage, and you can watch the recording of all the previous seminars in our YouTube channel. We also encourage you to subscribe to our mailing list so that you can receive regular announcements. And if you are now watching this on YouTube, then you can find all these links by going to this M intersection phi logo that you find down there, and then going to the About section. And if you're watching this live now, then you can find this information in the chat. Okay, so
I have one request to make, Hal.
yes.
Could you not turn off your video? Because if everybody turn off the video, I feel like I'm speaking into the vacuum. And
yeah,
in
of course,
fact,
I
if
will
others
remain.
can turn on the video, I would appreciate that too.
That's good.
Thank you.
Let's do that. Okay. Okay, so that was an advertisement. So now it is our great pleasure to have Hirosi Ooguri from Caltech and Kavli IPMU. And of course, Hirosi needs no introduction. So let me only note that his name is Ooguri Hiroshi in the original pronunciation. That's very different. So today, Hiroshi is going to tell us about symmetry in QFT and gravity. So Hiroshi or Ooguri-san, could you go on?
Well, thank you. It's a pleasure and honor to give this talk and One Word IAMP Mathematical Physics Seminar Series. I very much appreciate this series that enlightened my life during the pandemic. So I'd like to talk about the symmetry in quantum field theory and gravity, and this is a broad title, but it's actually mostly based on my work with Daniel Haro at MIT, who is here. I'm standing next. And then this is Dan Fried and Shidong. And the talk has 5 sections. And the first 4 is based on my work with Daniel that I wrote 4 years ago. And then the last one is more recent one, and I will also mention some work in progress with my student and postdoc. So my motivation is to understand the nature of symmetry in consistent quantum theory gravity. And there have been lots of interesting things about gravitational theory that is different from ordinary field theory. So one might think that, well, gravitational theory is just one of the field theory. So you just have, in addition to scalar field or Maxwell field, you just have gravitational field with metric as a degrees of freedom. And in fact, you can write down low energy effective theory, Einstein, Hilbert term coupled to some finite number matter field, and that seems to be classically make sense. But you can ask, well, can such theory come as a low energy approximation to consistent quantum gravity theory? And surprisingly, there seems to be rather non-trivial constraint on low energy theory in order for that to come from consistent quantum theory. That does not seem to happen in ordinary field theory. In ordinary field theory, you can write down you can write down any low energy effective theory, provided that it's free of anomaly. And you can expect that to be completed in consistent theory. For example, you can write down the Lagrangian of pion, and then it's completed by QCD, for example. And but that does not seems to be the case in gravity. And so I want to understand what kind of conditions are there, and can we actually derive that with certain rigor? So that's what I would like to do today. So one of the such conditions that people have noticed for many years, is go back to John Wheeler half-century ago, that consistent quantum theory of gravity does not seem to have global symmetry, exact global symmetry. So any global symmetry that your low energy effective theory may have has to be either gauged or broken by some quantum gravity effect. So here is a standard argument that I would like to present. Suppose you have a global symmetry, and here I assume the global symmetry is a regroup, compact regroup. And so it's a continuous. And so if you have a continuous regroup, then you can have arbitrarily large representations. So for example, if you have SU2, you have spin J representation, which has 2J plus 1 dimensional dimension. And then J can be arbitrarily large. So suppose you make a black hole with arbitrarily large representation. You can make that by combining matter field appropriately. But then you can Hawking radiate this black hole. It happens, but if you combine general relativity with matter field and semi-classically quantize, as Stephen Hawking told us. But if it is a charge with respect to global symmetry, the Hawking radiation is neutral with respect to this charge, which is different from the case of gauge symmetry. In the gauge symmetry, you have long-range interaction. And for example, if you have U1 gauge symmetry, you have plus charge and minus charge. And then that is discriminated by Hawking radiation because there are interactions between the charges. That does not happen in global symmetry. So low energy effectivity theory tells us that Hawking radiation is neutral, G blind. So that means that the representation is preserved. So eventually you get to the point where the dimension of the representation is bigger than the number of quantum states you can possibly have, as predicted by Bekenstein-Hawking entropy formula. Bekenstein-Hawking formula tells you what's the dimension of the Hilbert space of the black hole. And if it is smaller than the dimension of the representation, that's in contradiction. So that's a standard argument that people make. And there are other arguments, but this is one of the nice ones. But this argument has several loopholes. I'm not going to elaborate on this, but there are known loopholes. And also it doesn't apply to finite group symmetry. For example, if you have Zn symmetry, all the representations are one-dimensional. So this argument does not apply. Okay. So what can we do? Can we make a more sort of rigorous argument for the absence of global symmetry? So that's what I would like to do. So from here on, my slide is going to become handwriting. That just signals that it's going to be end of the introduction. So now, so I'd like to talk about, first of all, this is a review basically of what global symmetry means in quantum field theory without gravity. So I'm just reviewing the standard thing about quantum field theory. So I'm sort of hesitant to do that because I know many of the audience here are mathematical rigorous, as the name suggests. And so I feel like there's a saying in Japanese, preaching mantra to monks or something like that, shakani seppo. And but that's what I'm going to do. Okay, so I first want to define what the quantum field theory has as symmetry, global symmetry, not gauge symmetry, global symmetry. And assume that you have a global Cauchy surface with time. So suppose you have this kind of global split of space and time. And then, so here is my definition of what global symmetry means. First of all, there must be a unitary homomorphism from group to unitary operator, space of unitary operator on the Hilbert space of this quantum field theory. Okay, I could have said that it's a representation, but I don't want to say that because actually the statement I'm going to present, derived later, applies to spontaneously broken global symmetry. So in which case, actually it's not really a representation, but it's just a homomorphism. So I just wanted to relax this condition for the sake. But if you are interested in unbroken symmetry, then this can be just a representation. And I wanted to preserve the algebra of local operator on any region. So A of S is algebra of operator localized in subset of this Cauchy surface. And I want the symmetry to preserve. So that means that the symmetry won't change the location of the local operator. And I want it to be faithfully represented in the space of local operator. Okay. So this is important. So that means that the group cannot be arbitrarily large. Otherwise, we could have said that, for example, standard model of particle physics has monster group symmetry. And we usually don't say that because it's trivially acting on the standard model. Okay. And being symmetry means that it commutes with energy momentum tensor. So in a more modern way of stating it, it's a topological surface operator. Okay. So this is a definition. This is fairly standard. And what is going to become important in my talk is the splitability of symmetry. So this is a concept that probably is familiar to people who are not, to people in algebraic quantum field theory, but may not be so for other physicists. I just wanted to clarify that. So splitability of symmetry basically is a generalization of the Noether theorem. So let me remind you what the Noether theorem says. So suppose you have a continuous symmetry, then there is a Noether theorem, which says that there is a Noether current, which is a current operator, whose integral over Cauchy surface generate this operator U. Okay, so this is a Noether theorem that we learned in the first year in graduate course of quantum field theory. Okay, so this means that since this is exponential of integral of local operator, you have this kind of split property. That is that suppose you consider some disjoint sum of local region open set in the Cauchy surface, and we can consider disjoint sum of these things. Then it becomes product of operator, each of these acting on these regions, each one of these regions. So this is of course obvious because it's an integral over surface. So if it is integrated over a union of these joint regions, they integral split into these regions. So that means that it becomes product of operator. So since this is local operator, so different point of commute with each other, so you can just split into the local operator. Okay, so this you may call it the split property of symmetry generally. Okay, and this is true for continuous symmetry. Now, it was actually shown by a book called Doppler and Long, so they are algebraic quantum field theory people. We learned this from Ed Witten. Ed Witten told us when we were working on this, that this theorem might be useful for you guys. And he is indeed right. And so this was very helpful for us. So they pointed out that this property actually holds not only for continuous symmetry, but also finite group symmetry or discrete symmetry. Okay? And provided that quantum field theory has a split property. So this is a theorem. So if quantum field theory has a property called split property, then symmetry generator splits. Okay? So this split property is important for the rest of the my talk. So I would like to actually spend the next slide explaining what the split property is. Okay? So here is a definition of split property. Split property means the following things. So suppose you have two open sets in the Cauchy surface in such a way that closure of S is interior of S prime. So then the quantum field theory is split for every pair of S and S prime like that, that there is actually a type 1 factor in between the algebra of local operator of S and S prime. Okay, so this is what is called split property. So you can see that you have small region S and slightly bigger region S prime. And of course, the algebra of local operator in S is a subset of that of S prime. But there is something in between. And something in between can be type 1 factor. And if that is the case for every pair like that, then we say that quantum field theory splits. Okay. So again, this is not very useful thing for many of the audience, but I just wanted to remind you that for Neumann algebra acting on this operator space of linear operator on the Hilbert space is called a factor if its center is trivial. And it is type 1 if and only if it contains minimal projection. And type 1 factor is something that is very, very nice. So for example, it means that you can actually define the action Hilbert space in such a way that it's split into the one that realizes this operator and its commutant. So the Hilbert space actually split with respect to this type 1 factor. And unfortunately, and this is one of the interesting things about algebraic quantum field theory, the space of local operator is not a type 1 factor. So that causes all sorts of complications. So for example, if you go to the talk by physicist, string theorist on ADS QFT correspondence, And they talk about the famous Ryu Takayanagi formula, for which the Nishina Memorial Prize was given, and Breakthrough Prize was given. They say that, well, you have a quantum field theory, and you divide the Cauchy surface into two segments, and then Hilbert space split into product of Hilbert space over the space, subspace and its complement. And that's absolutely not true, because algebra local operator is not the type 1 factor. But this is the best possible thing that you can do, which is that there is something in between S and S prime, which is a type 1 factor. So that means that if you thicken this region a little bit, then essentially what Ryu and Takayanagi did in defining this entanglement entropy is correct. And so this is a better way to say it. And this works for many quantum field theory. And for this quantum field theory, there is this theorem by Buchholz, Doppler, and Rom that that symmetry generates a split. Okay, but unfortunately, this is true for many quantum field theory, but not true for all the quantum field theory. There are interesting counterexamples I would like to tell you about. So, for example, here is a counterexample. Pure Maxwell theory. So this is one of the simplest quantum field theory you can think of. It's actually free theory. So you just write down the Maxwell Lagrangian, U1 Maxwell Lagrangian, and that's it. No charged particle, okay? And suppose you define it on the Cauchy surface, which is a circle times some compact space. So it's D minus, so I'm defining D to be space-time dimension of quantum field theory. So it's D minus 1 dimensional space. And I think of this as like a torus, where you have S1 direction and complement, orthogonal direction, also transverse direction, which is also compact. So now, why this is not splittable? Why this doesn't have a split property? The reason is that if you consider electric flux over this compact direction, and you call this as phi, this commute with all the local operator because there are no charged particles. Okay, so it's the only charged particle here is electric flux. So that means that the phi is in the center of the algebra. If there is the type 1 factor here between here, so I'm drawing S and S prime. So here is there must be type 1 factor. So suppose you have a type 1 factor, then the phi is in the center. But phi is actually non-trivial operator. Flux is non-trivial operator because you can define a Wilson line, Wilson loop going in this S1 direction. And that has non-trivial commutation with this electric flux operator. So that's a contradiction. So that means that this quantum field theory does not have a split property. And if you are familiar with a more modern language of symmetry in quantum field theory, you may realize that this trouble is caused by the fact that this pure Maxwell theory has exact one-form symmetry, which is essentially generated by this electric flux. And this one-form symmetry is broken as soon as there is a charged particle. And when you have a charged particle, this property also gets restored. That is that phi is not, if you have a charged particle, phi is not in a commutant anymore because it doesn't commute with a local charged operator. Okay. So here is what I said. If the gauge group is compact, one split property can be restored by adding heavy charges in the ultraviolet. And in fact, the pure Maxwell theory has lots of funny properties, and these are all related to this non-split property. For example, if you consider sum of two Maxwell Lagrangian, you have two gauge fields, A1 and A2. And suppose there are no charged particles, then gauge group is R times R. Then you might think that there is a rotation symmetry to rotate these two Maxwell fields. And you can actually show that there is no gauge invariant net current for such symmetry. So because this symmetry does not split either. Okay, so this is like a counter example. But you notice that this counter example is constructed with this non-trivial topology. So in fact, so here is a recap. So just to remind ourselves, the quantum field theory is called split if there is a type 1 factor between the algebra local operator in this overlapping in this in this kind of regions. And the type 1 factor is nice thing because with respect to that, he will space split. And but if you talk to algebraic quantum field theorists, most of them say that, well, this is just because you have this non-trivial topology that for Euclidean space, we expect that any quantum field theory splits. For example, this Maxwell theory splits on this Euclidean space. And if you have conformal field theory, which I'm going to talk about next, then in fact, you can also consider sphere, because these two are conformally equivalent. So whatever happens, hold here, hold here. Okay, and this is sufficient for our purpose because we are just going to talk about conformal field theory on sphere times time. Okay, any questions so far? Okay, everybody's clear? Too trivial maybe because this is the kind of things that many of you are familiar with. Now I would like to go on to define global symmetry, talk about global symmetry in quantum gravity. Okay, so this is a difficult subject to talk about because I first want to give a reasonable definition of global symmetry in quantum gravity. But then in the next section, I'm going to prove that such a thing does not exist. So somehow my task in this section is define a reasonable looking notion of symmetry in quantum gravity in such a way that we can prove that it does not exist. Okay, so I have to strike a good balance between them. And so here's what I want to do. So I want to think of, the way I want to think about is that suppose you have low energy effective theory of gravity. And I'm talking about this in the context of ADS QFT correspondence. So you have a gravitational theory in unitary space. Unitary space spatial section is a hyperbolic space, so I'm drawing it on like a disk. And on the boundary, you have a conformal field. Okay, so that's the standard ADS QFT dictionary. And suppose you have some low energy effective theory in the unitary space, which has Einstein gravity coupled to matter field. And suppose this low energy effective theory has global symmetry. So that means that it acts on some local operator in local fields and preserves the Lagrangian and Hamiltonian and all that. But for example, the charged operator might be charged black hole, for example. So we must accommodate for such a possibility. But fortunately, in the context of ADS QFT correspondence, any of such excitation correspond to some local operator in conformal fields. So if you consider some low energy effective theory where you have some local field and you have black hole and other quasi-local thing, any finite energy state correspond to some local operator in conformal fields. So that means that if you have symmetry in gravitational theory, that symmetry must act on the local operator in conformal field theory and go back to the definition of symmetry of quantum field theory. So that means that global symmetry in gravitational theory in unitary space must correspond to some global symmetry in conformal field theory dual. But we need more conditions. And so I'm listing conditions. So here's my definition of what global symmetry in quantum gravity in unitary space means. First of all, it has to be a global symmetry of the dual conformal field theory. And it has to act locally on local operator, quasi-local operator. So that means that it can be a local excitation of field, or it can be a black hole or something like that, but with finite radius, finite horizon size. If the horizon becomes too big, then in the case of unitary space, the size of the horizon grows with energy. So eventually it touches the boundary, but that would require infinite energy. If you are familiar with gravitational theory, you might object that there is actually no exact notion of local operator in gravitational theory because it violates the diffeomorphism invariance. But ADS QFT correspondence has taught us that there is a procedure called gravitational dressing. Just like in the case of gauge theory, you don't have a charged local operator, but you can make a quasi-local operator by attaching Wilson line to the charged operator. You can do similar thing for gravitational theory, and you can define actually quasi-local operator that way. And but gravitational dressing is charge neutral. So you can assume that the addressing part is not relevant to the leading order in the calculation. And so we can say that it should act locally on quasi-local operator. And it should also, the action should also be faithful. So that means that for any symmetry generators, there must be some non-trivial operator in the bulk which transform non-trivial. Otherwise, it doesn't make sense to call that as a symmetry, just like I said. Otherwise, standard model particle physics may have monster symmetry. Okay, and we also want to distinguish that from conformal symmetry on the boundary. So conformal field theory, of course, has a conformal symmetry, but that actually is gauge symmetry from the gravitational point of view. That you have diffeomorphism symmetry, but in unit space as a boundary, so you can ask where. So there is a situation where some of the global diffeomorphism symmetry, which is a gauge symmetry, acts non-trivially on the boundary, and that acts as a global symmetry, which in this case is a conformal symmetry. So it's actually a gauge symmetry. Okay, so we are not going to include this as a part of the symmetry. Okay, so that's my definition, and I hope this sounds reasonable to you. And because then I would like to prove that such a thing does not exist. Okay. So here is my outline of, but before we go there, is there any question about my definition of global symmetry in quantum gravity? Okay. If not, I'm going to move on.
Excuse me.
Yes.
What is meant by gravitational dressing?
Yeah, so I briefly explained it. If you're in the diffeomorphism invariant theory, there is no strict notion of local operator because it's not gauge invariant. But gauge theory has taught us how to deal with this. Because, for example, suppose you have a gauge theory. Suppose you have, say, for example, a QED. The electron field is not a gauge invariant operator, because it transforms under gauge transformation. So if you put the electron operator somewhere, then that is not gauge invariant operator, but you can make it gauge invariant by attaching Wilson line to and send that endpoint to infinity. So that's usually what we think about the electron field. And we can do the same thing for gravitational theory. So gravitational theory is example of gauge theory. So there is actually a generalization. There is a gravitational version of the Wilson line, which you can attach to local operator and make the local operator gauge invariant. That's what is called gravitational dressing. That's the definition of gravitational dressing. Okay, and this gravitational dressing is made entirely in terms of metric field. So therefore, when you have global symmetry, which does not act on the geometry, then it's commute. The gravitational dressing part is not relevant for the discussion of global symmetry. Okay.
Thank you.
Okay, so now I would like to prove that such a thing does not exist. Okay, and then that makes use of what is called entanglement wedge reconstruction. And this is actually a very profound concept. And I'm afraid I won't be able to do justice to this during this talk. But I just wanted to briefly describe it because this is a key ingredient of my proof. So here is the idea. So you might have heard about ADS CFT correspondence, which means that some local excitation in the bulk of ADS in the gravitational theory can be described in terms of Hilbert space on conformal field theory on the boundary. Okay, so the ADS CFT correspondence says that anything that happens in ADS can be described in terms of Hilbert space and time evolution on the boundary conformal field theory. Okay, but in fact, there is a more refined version of this correspondence, which became clear during the last 15 years or so after the discovery of Ryu-Takayanagi formula, which is more refined version in the following sense. So Ryu-Takayanagi formula says that suppose you choose some region, say here, I have divided the boundary of uncertain space where conformal field theory lives into 3 segments, A, B, C. So I'm considering this as a union, boundary Cauchy surface as a union of A, B, C. So suppose you consider region A union B, B union C. Okay. So there is this thing called Ryu-Takayanagi surface, which is a minimum surface in the Bark, subtending on the boundary of B union C. Okay. So this is a Ryu-Takayanagi surface. So there is this red region, red shaded region, sandwiched between this Ryu-Takayanagi surface and the original boundary region. And refined version of the ADS QFT correspondence, which is called the entanglement wedge reconstruction, says that anything happens in this red region can be understood as operation on B union C. So by using this split property, etc., you can roughly define some Hilbert space associated to B union C. And then you can describe whatever happening in the red region by Hilbert space on B over B union C. Okay, so this is called the entanglement wedge reconstruction because this shaded region is called the entanglement wedge. Okay, so but this leads to some interesting paradox. So for example, suppose I pay attention to this gray dot in the middle. Okay, so this gray dot is in the entanglement wedge of B union C. So that means that this operator can be described in terms of some operator over B union C. But it's also in the A union B. So that means that there must be some operator on A union B that describes this. And then also it's in A union C. So that means that it must be described in terms of A union C. Okay. So that means that this gray operator does not have a unique description in terms of operator in conformal field theory. There is some kind of ambiguity in identifying what this operator is, because it can be an operator realized on B union C, or A union B, or A union C. There seems to be some redundancy in the definition of this operator. So that's a sort of interesting feature that understood. And there is another interesting feature. So we can consider complement of this. So you can think of this white region now as the entanglement wedge. Okay? You can regard this white region as the entanglement wedge of A. You can regard this region as this white region as the entanglement wedge of B. You can regard this region as the entanglement wedge of C, for example. Okay? So that means that whatever happens in this white region can be understood in terms of local operator in A. Whatever happens in this white region can be understood in terms of local operator B, etc. But in the complement cannot be encoded in A. So now here is a puzzle. Here is a puzzle, and I would like to pose it to you. So this gray dot. So suppose you have this local excitation in gray dot. That cannot be described in terms of this region A, because its entanglement wedge does not cover this gray region, right? Similarly, it cannot be described in terms of B, because it's in the over here, and similarly C. So that means that this local excitation cannot be described in terms of Hilbert space over A, Hilbert space over B, or Hilbert space over C. But nevertheless, is describable in terms of the entire Hilbert space. So how can this happen? So here's the puzzle. The resolution to this puzzle is the fact that indeed, if you go deep into the anti-theta space, information about local excitation is encoded in the entanglement information between these regions. So namely that this, for example, if you consider B union C, you can actually encode this information. But if you consider B or C separately, you cannot encode this information. So that means that the local excitation in anti-theta space is encoded into entanglement information on the boundary. Okay. This actually turned out to be, and this is an insight by Daniel Harrow, that this turned out to be very closely related to what is called a quantum error correcting code in quantum information theory. So when you build a quantum computer, you want to make sure that error can be corrected, just like in classical computer. But in quantum computer, it's very important because quantum coherence can be easily lost. And you want to make sure that it can be maintained when you do the calculation. In classical computer, the way you do it is to introduce redundancy. So you make many copies of the same information, and you do the things like parity check. And you have more elaborate things like Gore code or something like that to make sure that the error can be corrected. But you cannot use that trick in quantum computer because there is a thing called the quantum no Xerox machine principle. It says that there is no unitary operation that maps a single vector into a tensor product of the same vector. So you can't do that. But what you can do is consider various copies of the product of Hilbert space and encode quantum information in the entanglement of these Hilbert spaces. And it turns out that this is exactly what the ADS-CFT is doing. And that is one of the reasons why actually many ideas of quantum information theory have become very important in holography and the ADS-CFT correspondence. This is one of the important things. So I'm going to use this idea to prove that such a thing does not exist. So here's the proof. So suppose to the contrary to what I want to prove, that gravitational theory in anti-theta space has a global symmetry. And according to my definition, there must be a quasi-local bulk operator which transforms phase-free under the symmetry. So suppose I put such operator in the middle. Now, suppose I divide the boundary into segments in such a way that each of the entanglement region for each of these regions does not touch this operator. But symmetry is split. So that means that the symmetry generator of this Cauchy surface split into product of a unitary operator acting on these regions separately. Okay, and so that means that since this does not cover X, so this U of R1 commute with X, U of R2 commute with X, etc., and everything commutes. So that means that this unitary operator must commute with this local operator located in X, which contradicts with the premise that it has to, this local operator has to realize this symmetry phase. So that's a contradiction. Okay, so this is a one-page proof that such a thing does not exist. Okay, so if you want to understand the proof developed fully, you should look at my paper with Daniel, which appears in GMP, the 175 pages. If you are not that patient, you can read a physical regulator paper, which is 5 pages. There's 35 times the encoding of the information and compression of the information. Anyway. Okay, so I just wanted to point out that I said that this idea of quantum information is very important in ADS-CFT correspondence. So it's not surprising that actually there is a counterpart of this statement in quantum information too. And it's called actually Easton-Knull theorem. And that is a statement that suppose you have this error correcting code like that, where you have a logical qubit and you have a physical qubit. And the statement, so basically you encode this information in logical qubit into product of this physical qubit. And then the statement is that there a non-trivial operator unitary operator acting on this logical qubit can be expressed as a product of operator acting on the physical qubit. And this is sort of counterpart of this theorem. I'd like to mention a few comments about this statement. So this argument actually applies also to spontaneously broken gauge global symmetry. So this means that, for example, so if you have a spontaneously broken global symmetry, then there is a scalar field for which the global symmetry acts as a shift operator. But that cannot be exact symmetry according to this theory. So that means that this shift symmetry has to be broken at some point. So this is very interesting because this kind of symmetry is used to build model in cosmology, such as the inflation model. And so this theorem says that, well, you can't do arbitrary thing. Eventually, this symmetry must be broken. This argument also works for, so I said specifically that I don't want to consider space-time symmetry, but in fact, this theorem, this statement actually works also for discrete space-time symmetry, such as parity or time reversal. So this means that actually the parity or time reversal symmetry in gravitational theory cannot be global symmetry. It has to be gauge symmetry. Okay? It's not obvious because it's not a continuous part of the field. So in fact, it has a physical consequence. When you quantize gravity, you are supposed to sum over geometry. But you can ask, what kind of geometry we are allowed to sum, or we are forced to sum? Okay? So for example, if parity is a global symmetry, or time reversal symmetry is a global symmetry, then you would have a choice of not summing over non-orientable manifold. Or you can actually introduce some kind of chemical potential to distinguish this kind of summation. This theorem says that you cannot do that. You have to sum over non-orientable manifold. Okay? So this is non-trivial statement. This argument does not work for all dimensions, because here I specifically assume the Einstein gravity coupled to matter field. So for example, two-dimensional gravitational theory can have global symmetry. So for example, the two-dimensional theory on the worldsheet of string is a gravitational theory, and it can have global symmetry. So for example, worldsheet theory of heterotic string with E8 cross E8 or SO32 global gauge symmetry. From the point of view of worldsheet, these are global symmetry. So these are like a counterexample. So this theorem works for 4 or higher dimension with Roy-Energy effective theory described in terms of Einstein gravity. Okay. I also want to briefly talk about
Hirosi, can I ask a question? So I understand this R1, R2 that are the region in this CFT boundary, and how do you choose? So can you just simply split the surface into arbitrary regions?
So I'm assuming that you have the split property. So I just divide the boundary into these unions, and then I just choose them. I just choose them in such a way that entanglement region of any one of these does not cover this.
But if you make it, if you divide it into very, very small regions, then this entanglement which only covers the very close neighborhood of the boundary. So this gray region doesn't go deep into.
Right. So that's important because I could have moved this X to the very close to the boundary, but then I have to divide this boundary into very small regions so that it won't cover. So this guarantees that you can put X anywhere, and it's also always commute with this local operator.
Another question, may I? The question is how this argument works in de Sitter space and not anti-de Sitter.
No, I don't know. This assumes anti-de. So I'm just proving the theorem in ADS CFT context.
Yeah, and because it's, phi into phi plus constant.
Description in de Sitter space, then it might work. But I have a question of whether quantum gravity in de Sitter space exists or not.
Yes. So I'm talking about the argument that phi into phi plus constant is certainly broken, but it may be not so in de Sitter space.
You can prove any theorem for the object that does not exist. So if you prove that the de Sitter space does not exist in consistent quantum theory gravity, then this theorem is true for that space.
Okay, but then we have a problem since we live in de Sitter space.
No, well, do you know?
I think
we know that we are living in accelerated universe, but the nature, for example, the equation of state of dark energy is not known. And this is going to be studied in the coming decade.
Okay.
So I think it's too hasty to say that we live in de Sitter space. We live in the space with positive dark energy, and the universe expansion is accelerating. That's the only thing we know for sure. We don't know the equation of state of dark energy.
But as Roger Penrose argues, it is a very beautiful space-time, which is de Sitter. So I believe in that.
Yeah, and the Euclidean space is a beautiful space, but we don't live in it.
It's not that beautiful if you write a Penrose diagram for
Beauty
that.
is not the only criteria.
Yes, absolutely. Yeah, that was just a question about.
Beautiful world in the Platonic world of mathematics, which
yes.
are not.
Okay, thank you.
May I pose a question?
Yes.
I think the problem with your argument is that you assume that these unitaries are elements of the algebra of observables. But in case you have a non-abelian global gauge symmetry, there's no reason why these unitaries should be elements of the algebra of observables. So it's not clear why the split property should hold for them.
Well, I'm not sure why did I assume that U itself is in the algebra broker operator. I only assumed split property, which is.
Because you assume the split property for these unitaries.
Well, I'm assuming that U is a unitary operator. Yes.
Yeah, but I think it's not.
And this works for no-abelian symmetry. I don't understand your point.
So in.
At what point did I assume that symmetry is abelian?
So when you have a global symmetry, then it's not clear that you have these unitaries can be obtained in this way.
In which way?
So the global symmetry would in algebraic quantification consider to be a certain superselection sector, existence of non-trivial superselection sectors. And the existence of these unitaries is an additional property which holds under certain conditions. When you look at the Doppler-Haack-Roberts theory.
Okay.
But the assumptions of the Doppler-Haack-Roberts theory are not always satisfied. So for instance, it's known that in massive theories, you can prove that there's this duality axiom of Doppler-Haack-Robert, but this duality axiom is not always satisfied.
Okay. Well, I wasn't aware of this. I need to understand it. You could provide me some reference on this.
Yeah. I think that was analyzed in the paper by Buchholz and myself.
I have the impression that there is some kind of linguistic misunderstanding between us, but it's very hard. It will be hard to resolve it in real time.
Of course.
Yeah, but maybe we can discuss it afterwards, because I think it's an important point. So it would be nice if there was something well, interesting there. I think we should maybe postpone.
Okay, so let me move on. So I would like to discuss completeness of gauge representations. So I have proven that global symmetry cannot exist in gravitational theory in unit space. So that means that any symmetry is either broken or gauge symmetry. So suppose you have a gauge symmetry, then there is another expectation just formulated by Joe Poltinsky most clearly, which says that if you have actually a gauge symmetry in gravitational theory, then all possible unitary irreducible representations should appear in the Hilbert space that's consistent with Dirac quantization, etc. And that is not necessarily the case for quantum field theory, but it is a case for gravitational theory. And so you can actually easily come up with an example of quantum field theory where some representations are not realized. But it's actually the case for gravitational theory. So I would like to prove this. Okay, so to prove this, I would like to first make a preface that in the standard ADS-CFT correspondence, we say that if there is a gauge symmetry in the bulk, there is a global symmetry on the boundary. But one can ask, well, are they the same group? So for example, could it be that the symmetry on conformal field theory is SU2, but symmetry on the gravitational theory is SO3, for example? They look similar, but they're actually not the same. So in order to show that they are the same symmetry group, we need to show that any operator, any symmetry algebra of the conformal field theory acts faithfully in the bulk operator in gravitational theory. And actually, we can prove that this is the case. So here is a proof. So to do that, first I would like to do the following thing. So suppose you have a gauge field in the bulk, the gauge symmetry in the bulk. Then there is a Wilson line operator. And the Wilson line operator can be constructed for any representation. So suppose you have a black hole. Suppose you have an eternal black hole. Then there are two asymptotic regions. So on the one asymptotic region, you have untheta space, and you have a boundary, and you have a Hilbert space for the conformal theory. And there is another asymptotic region connected by Einstein-Rosen bridge, where you have Hilbert space of conformal theory. Okay? So you have actually tensor product. So suppose you have this, suppose your Wilson line actually goes through this wormhole, Einstein-Rosen bridge, inside of the black hole in ADS. Then you have these two endpoints of the Wilson line ending on this Hilbert space endpoint. So this Wilson line operator acts as a representation alpha in this conformal field theory on the left, and then acts as it's a dual on the conformal field theory on the right. So suppose you act unitary operator, conjugate this by unitary operator acting on the left Hilbert space, then it makes a representation, and it's a standard theta-wire theorem that for any group element there is a representation for which this matrix element is not trivial. So this means that there is an actually operator you can define in the bulk, which transforms non-trivially for every group element. And so that means that the ADS gravity actually represents this global symmetry on the conformal field theory faithfully. And that, if once you have this faithful representation, then you can actually consider product of these things to generate any finite dimensional irreducible unitary representation of the group. This is actually a simple group theoretical theorem, a lemma that you can prove. So this proves the completeness hypothesis. Okay. So this shows that in the gravitational theory, in fact, all possible unitary representation appears. But this is not totally satisfactory. This is what Joe Polchinski said, and we proved it. But this is not totally satisfactory because it doesn't tell you how the Hilbert space gets decomposed into this representation. So this is something we actually did recently last year with Daniel Howe. So we did that for finite group symmetry, and I'm going to tell you what happens for continuous regroup symmetry. But let me first talk about finite group symmetry. So here is what Daniel and I proved. Suppose you have a conformal field theory which has gravitational dual. These are called holographic conformal field theory. So suppose it has a global symmetry with symmetry group being finite group. But then we proved using the holographic description of conformal field theory that if you consider this what you may call twisted partition function, or mathematician would call twine partition function, which is that consider this partition function e to the minus beta h. Beta is the inverse temperature, h is a Hamiltonian. Insert this symmetry operator u of g, with small g belong to this group. Then we show that when beta becomes small or temperature becomes large, then it's actually proportional to the original partition function with delta function in group area. Okay. So I'm going to show you in the next slide a proof of this statement. But this is an interesting. So this means that since the delta function in the finite group is actually written in terms of sum of a character of representation. So this statement is equivalent to say that if you consider a very high energy state of this conformal field theory and pick one state randomly from this Hilbert space, then the probability of that state to belong to a representation alpha is given by this formula. Okay, so namely that each representation occupies this fraction of all possible states. Well, so it's actually interesting. It's proportional to square of dimension, and of course, just follow from standard finite group theory, representation theory. The sum of all the representation of finite group of this sum up to 1. So it's consistent with being probability. Okay. So now how are we going to prove that it's proportional to delta function? So here is an argument. So in high temperature, if you have a holographic dual, in high temperature, you get the black hole. So this computation is a Euclidean computation. So you have a Euclidean circle of radius beta, and inside of it is a black hole, okay, Euclidean black hole. So one of the things about the Euclidean black hole is that it's contractible in the circular direction. Is contractible to a point because there is a horizon in the middle. And so here is an idea. So suppose we consider Wilson line in some representation alpha, and it starts and end on the boundary. And suppose these endpoints are very close to each other, then this Wilson line becomes trivial and it becomes proportional to the delta in the representation space. Okay. Now, but this is a finite group, so finite group has no curvature. So I can move this endpoint to over here. And here I use the fact that the bulk is a Euclidean black hole. So there is no, the bulk circle is contractible, boundary circle is contractible. So I can actually move this over here and make this very close to each other. And then, but then this endpoint can jump on the other side. So when you jump on the other side with this unitary operator representing the group, then it gives you a representation matrix. So you get an identity that Kronecker delta in the representation space minus the group representation element multiplied to this partition function vanishes for any representation. Okay. So you can ask, why is that possible? Can you solve this equation? And of course, you can solve this equation only if you postulate that this partition function is proportional to Kronecker delta function in the group. Because if it is this is proportional to delta function in the for the group, then this becomes trivial, and then this vanishes. So this is a solution. Okay. So this is a very simple derivation. So this derivation does not use the detail about the gravitational theory, but just the idea that some circle become contractible at high temperature. So this led us to expect that this holds for a larger class of quantum field theory. And in fact, it was proven that in 2-dimension conformal field theory, this is actually a true statement for any unitary conformal field theory. You can actually prove that by using modular invariance. And more recently, a couple of interesting papers appeared after this. One is in the language of algebraic quantum field theory, that by assuming, they assume certain property of some field double states, and other assumptions, they actually derive this for any conformal field theory. And it was also shown by my colleague at IPMU that this is true for any weakly coupled quantum field theory. So this seems to be true for wider class of quantum field theory. It's interesting to understand. So this is for finite group. So you can ask, well, what happens if it is a regroup? Well, regroup is a little bit of a challenge because, well, if you look at this formula, then this G is the number of elements of the group, and of course, regroup is infinite. And also the number of representations is infinite. So you cannot sum this to 1, become divergent. So the denominator is infinite and numerator is infinite. So you want to understand what happens for to make this regularized. In fact, for regroup, it's actually a regularized version of this statement, which actually recently I found with Monica Khan and Jai Hari. We are writing a paper about, and basically we prove that for finite group symmetry, what happens is that the probability of finding state in particular representation is again proportional to square of dimensional representation. But there is actually this Gaussian separation factor, exponential proportional to the second Casimir of the representation with temperature. So for very high temperature, for small representation, it's actually proportional to square of the dimension of representation. But then representation becomes very large, then it starts decaying like a Gaussian. Okay. So temperature gives you a cutoff on the size of the representation. So this actually we verified using holographic conformal theory and also weakly coupled conformal theory. Okay, so that's all I wanted to tell you. I just wanted to pose some question for the future. So I proved that any global symmetry in low energy effective theory in quantum gravity must be either broken or gauged in disguise, but it doesn't tell you how it is broken, or if it is actually gauged, what the strength of the gauge coupling, etc. So we'd like to understand this. And for example, completeness of gauge charge means that there is actually a charged state for any representation, but it doesn't tell you how heavy those things are. And it would be interesting to find out. So for example, in phenomenological application of this result, it's important for both of them. And somebody asked digital space. I don't know if digital space exists, but if it exists, we want to extend this proof or negate, come up with a counterexample to this proof. And I think what requires is a generalization of the notion of holography. So if there is a holographic description of digital space, we might consider generalizing this line of derivation. Okay. So that's all I wanted to say. Thank you for your attention.
Thank you very much, Hirosi, for a very interesting and exciting talk. And we already had some interesting questions and discussion during the talk, but I think we want to take questions. So, okay, yeah, why don't you go on, Fabrizio? Please unmute and ask question. Oh, it was not a question.
Yeah, sorry, I was just thanking for the talk. Sorry.
Oh yes. Any questions? No. Okay.
Can I ask a question?
Please. Sure.
Yeah. So yeah, thanks for very interesting talk. Although I cannot say I understood most of it, but so in the last part of your talk, you presented interesting result on something like finding the random state in conformal field theory belonging to certain representation.
Right.
And that seems to be very general statement for conformal field theory with symmetry.
Yes,
And
yes.
you had.
In fact, in 2 dimensions, it's actually a true statement for any conformal field theory.
I see. And so you presented a very nice proof based on ADS CFT, but so is this result, can it be understood without ADS CFT?
Yeah, so I actually, the proof in 2-dimensional conformal field theory, well, first of all, if it is true for conformal field theory, it's true in quantum field theory because we are talking about high temperature limits. So
right.
any theory can be considered as a conformal field theory. But in 2-dimensional conformal field theory, the proof is very simple. So let me actually give you a proof, okay? So consider this kind of things, twisted by G, okay? So do the modular transformation.
Mm-hmm.
So if you do the modular transformation, then so here so in 2 dimensions you consider 2-dimensional torus, and then so here the twisting is happening in Euclidean time direction.
Yeah.
But if you do the modular transformation, twist happens in the spatial direction.
Right.
And so then you can, so high temperature limit correspond to the just like Cardi showed. High temperature limit in that modular transformation after the modular transform becomes understanding the ground state energy. So all you need to show is to show that ground state energy of the twisted sector is higher than that of the vacuum state. Because if that happens, then if you have G is non-trivial, then its energy is bigger than that of the ground state. And so therefore, the contribution from non-trivial element, group element, is exponentially suppressed in high temperature limit. But then you can actually prove that for unitary conformal field theory, twisted state has energy higher than the ground state energy. And so that's sort of. For example, this also holds for, so in fact, the proof is even simpler for continuous group in that case. So because in the continuous group case, there is actually standard Gepner-Q representation of conformal field theory where you can write any Hilbert space of any conformal field theory as sum of product of representation of U1 part and the rest, like parafermion representation. And then twisting by G, you can actually first diagonalize G to make it in the abelian direction, Cartan direction. And then twist by U1 direction is described in terms of twisted state in this Chu-Gepner representation. And so this is, so in two-dimensional QFT, actually, the proof is very simple.
I see. Very interesting.
And then more recent paper by, I have not completely internalized their proof, but there is actually an interesting paper by Megan following up on his earlier work by Cassini and the collaborator, where they claim to have proven this for a more general statement. So setup.
Yeah, thank you. Yeah, actually, I was using similar idea on maybe different, but maybe related problem like a Lipschutz-Matisse theorem and so on recently. So yeah, I will study these papers. Thank you very much.
Very interesting. So I want Klaus to, continue this discussion, but before that, I'd like to have more naive question, if any, from less professional audience, like me. So, okay, so I have a naive question. So you mentioned this proof, which is like 175 pages long. So what does it deal with mainly? So
mainly,
all, does this
so I think main thing the main part of this paper has to do with definition of symmetry. So we spent a lot of time, lot of pages in this paper explaining what symmetry is in quantum field theory.
So you're trying to prove sort of no-go theorem. So
yeah,
and so you're assuming
our assumptions are all spelled out.
So you are assuming ADS CFT correspondence and this Ryu Takayanagi and
so I have basically condensed this here. For example, I briefly talk about how we define symmetry here and quantum field theory and gravitational theory. And so most of the paper is about explaining this more precisely, more carefully.
Okay. Any other naive questions? Okay, so Klaus, do you think you can have fruitful discussion within limited time?
So the problem is that I'm not, of course, expert of algebraic quantum field theory. I'm user of this. So I have made use of their theorem. And so if you say that this theorem does not apply to abelian symmetry, I would be very surprised.
Klaus, you are muted, I think.
The description of symmetries you use is somewhat relies on certain assumptions. For instance, when you start so the starting point in algebraic quantum field theory is that you have different superselection sectors, and the observables are by definition gauge invariant, so they're invariant under the symmetries. And then you analyze these different superselection sectors.
Are you talking about gauge symmetry or global?
No, global symmetries. But global symmetries are not directly visible in terms of observables. What you directly see are the representations. And then you analyze the representations, and from them you reconstruct.
Could I pause? So, for example,
for instance, when you have say you have.
Can I inject a question before you go on? For example, in conformal field theory, we have this notion of state operator correspondence.
Yeah.
So that is that there, for every state there is an operator and vice versa. If symmetry is represented non-trivially on state, why can't it be represented non-trivially on operators?
So So the starting point is that you have a representation of your observables, and you compare different representations. And under certain conditions, you can show that there exist operators which intertwine between these representations.
Can you answer my question? Can you answer my question? What happens to conformal field theory? In conformal field theory, there is a state operator correspondence. For every state, there is an local operator. That's a well-known established statement which we have used for 50 years.
Yeah.
If the state is is in the non-trivial representation of symmetry, why aren't local operator being non-trivial representation of this symmetry? Maybe we are talking about different things.
Yeah.
That's my question. What's your answer?
Yeah.
Yeah. So at the moment, I cannot answer this question. So I don't know whether this is true for conformal field theory.
This is a crucial point. This is a crucial point.
Yeah, but
because
when you have a representation,
when I say that local operator is not transforming non-trivially under symmetry, I'm talking about in this sense.
Yeah.
So if you explain this, I don't understand your question.
Okay. So what I was mentioning was more general quantum field theory, not necessarily conformal field theory. So there this analysis had been done, and
but I'd be very surprised if this was a very special feature of conformal field theory.
Yeah. Okay. It could be that you in conformal field theory have better conditions. This might be. This I cannot comment on in the moment.
Okay.
But I would be very surprised that in conformal field theory you can have local operator which transform non-trivially and a global symmetry, but that does not happen in general quantum field theory. That'd be very surprising.
What I was appealing to was this general analysis of superselection sectors. And under certain conditions which were identified by Doppler-Roberts, you can, and then later by Doppler-Roberts alone, you can, from the structure of different of superselection sectors, reconstruct the group of symmetries and also the charged fields, which transform non-trivially. But these conditions are not always satisfied. This is what I wanted to say. And for instance, these.
So conformal field theory seems like it's always satisfied. So is this the case that this condition is satisfied for every conformal field theory?
I'm not sure at the moment. But that holds true for conformal field theory. But
yeah, that could be I don't know, but that could be a solution.
It could be a solution, yes.
Good. Yeah, thank you very much. So anyway, time is going, and actually Hiroshi and I are now in Wednesday.
Yeah, well, I'm totally fine. I actually switched myself during the talk. Switched myself to California time, so look like
okay.
Okay.
So, any other questions or comments? Okay, so if not, let's thank Hiroshi for his beautiful talk. Thank you very much.
And Klaus, maybe you can send me some reference I should study.
Yeah, I can write to you. Yes.
Yeah, thank you. I appreciate that.
Okay, fine.
Thank you very much.
Very good.
Thanks.
Okay.
Bye.
Bye.